right, in this Hughes Views lecture, I'm going to be talking about some general fatty acid nomenclature, and I'm pulling most of this information from your biochemistry book, chapter 9, section 2. So fatty acids are the simplest lipid out there. They have a general formula, which is COOH. So COOH is going to be this carboxylic acid over here, and the R group refers to this long hydrophobic chain. These molecules are amphiphilic, and an amphiphilic molecule or compound is something that contains both polar and non-polar regions, which is exactly what a fatty acid is. So it has a very non-polar hydrocarbon tail, and then a very polar head group, which is a carboxylic acid head group. This is a table from your book, table 9.1, and it lists a bunch of different common fatty acids as well as gives their melting point over here. But I want to draw our attention to a few fatty acids that you're going to have to memorize. Only 3, don't worry. And then how we shorthand that notation to make it a lot simpler to be able to think about and draw. So the 3 you'll have to memorize are going to be palmitate or palmitic acid, stearate or stearic acid, and arachiodate or arachioditic acid. So palmitate is 16 carbons long and has no double bonds. So it's a saturated fatty acid. Stearate or stearic acid is 18 carbons long, no double bonds, and then arachiodate is 20 total carbons long. That hydrocarbon tail is 20 total carbons, and again, 0 double bonds. Maybe the best way to remember this, or one little quick way, is that the S in stearate, you can draw like a straight line down it, and then it looks like the number 8, and that's your 18 carbons in your long chain. Okay, so a way that we like to write these fatty acids out is we typically do a number colon number, and the very first number will show you how many total carbons are in the fatty acid chain. And after the colon, the second number will tell you how many total double bonds there are. So for example, instead of saying palmitate, I could just say 16-0. So draw me 16-0 fatty acid. So you'd have to draw 16 carbons. Don't forget the carboxylic acid, but the 0 indicates no double bonds. There are a few examples where you can start to add double bonds in this list, and in a couple slides I'll go a little more into how we would denote that. So when you have a double bond, we can be very specific about how do we label that double bond in this kind of very shorthand nomenclature style. So you must memorize the common names for 16-0, 18-0, and 20-0 fatty acids. Okay, so on that slide, I was saying things like palmititic acid or palmitate, and stearic acid and stearate. So the ic acid for the verse 8. This is something we've already covered in class, but it can't hurt to reiterate it one more time. The carboxylic acid functional group, this ending refers to its protonated state. So if you hear somebody say something like palmititic acid, the ic acid would be the protonated form of the carboxylic acid. And if you hear somebody say palmitate or stearate, then they're referring to the deprotonated form. So this is just general nomenclature of things. Typically, the pKa of a carboxylic acid is going to be around 4 to 5. And so all of these fatty acids at physiological pH of 7, they will be in the deprotonated form, which is why mostly in your books you see them all being referred to as the 8 endings, like stearate, palmitate, arachiodate, things like that. All right, so talking more about nomenclature, let's talk about numbering and naming the different carbons in the chain. So first I'll kind of go over the IUPAC naming system. So here is our example here. It is a fatty acid that is 12 total carbons long. The IUPAC naming system, you would call the very first carbon the one with the highest priority or the more oxidized carbon. So carbon 1 is going to be our carboxylic acid carbon and not our really reduced carbon down here, the CH3, this little methyl group. So that's carbon 1, and then you just count, right? Keep counting now. 1, 2, 3, 4, 5, 6, 7, da 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 da. That's the IUPAC numbering of these carbons in the fatty acid chain. The Greek numbering, unfortunately, doesn't say that carbon 1 is the alpha carbon and carbon 2 is the beta carbon. In fact, the Greek nomenclature is in reference to its location against the carboxylic acid carbon. So the alpha carbon is the first carbon away from the carboxylic acid. So this would be the alpha carbon, the beta carbon, the gamma carbon, the delta carbon, the epsilon carbon. And I don't know what the letters really go after that. Typically in biochem, we never reach past epsilon, but maybe if you're in Greek life, you know the Greek alphabet. But the other one, though, that I do know is that the very last one, I am the alpha, I am the omega, I'm the beginning and I'm the end. So omega is always going to be your very last carbon. It doesn't matter where it follows in the Greek alphabet. Like, let's say we get all the way up to the letter, here's like M, N, this is an O, this would be the omega carbon, the last carbon. So you call this one the omega carbon. A little other bit of nomenclature here that's highlighted in this figure from your book is the fatty acid refers to this entire complex. So with that carboxylic acid moiety. A fatty acyl group, which typically is put on different things like the lipid anchor of a lipid anchor protein, that would be a fatty acyl group. And so that starts at this carbonyl carbon and then is the long fatty acid chain. Because typically now this carbon is not bound to this O minus, it's bound to something else, something completely different, like an amino acid or a cofactor, which we'll see coming up a lot later in the synthesis and breakdown of these fatty acids. So fatty acyl refers to essentially the C double bond O and then hydrocarbon tail. And then hydrocarbon tail does not include the carboxylic acid carbon, right? This is the hydrocarbon tail. So what would be an omega-3 fatty acid? You know that they're good for your brain and fish have a lot of them, or maybe you need to take pills, little over-the-counter supplements. So omega-3 fatty acids refer to the location of a double bond from the omega carbon. So here's an example of the linolenate, which is 18 total carbons long, but has 1, 2, 3 double bonds in it. So this would be an 18,3 carbon. It is an omega-3 because if you go all the way down to the omega carbon, the very last carbon, and you count backwards, it's 1 carbon, 2 carbons, and 3 carbons, there is a double bond right here that is 3 carbons from the end of the chain. So this would be called an omega-3 fatty acid. I guess also note, though, that that omega-3 fatty acid, it has to be between carbons 3 and 4 going this way. It can't be between carbons like 2 and 3. Then that would be an omega-2 fatty acid. So just keep that in mind. So omega-3 would be 1, 2, 3 away, and then heading more towards, you know, the first carbon, since we're counting backwards anyways, that's where your double bond will go. So between carbon 3 and 4 from the 3 and 4 from the end carbon, the omega carbon. Okay, cis versus trans fats, cis versus trans fatty acids. This shouldn't be really hopefully anything too new. This is a lot of organic chemistry terminology getting pulled into this lecture here, just applying it though to a biological molecule, fatty acids. So cis means same. So the hydrogens of that double bond are going to be on the same side of the double bond. And trans means opposite. So the hydrogens are opposite each other against the double bond. Nomenclature-wise, our shorthand way to tell where the different double bonds are is that they are going to be with this delta meaning there was like a change, and then a superscripted number. And that number tells you the carbon, the starting carbon from the IUPAC numbering system of where that double bond starts. So both of these over here are examples of delta 9 fatty acids. So here's our carboxylic acid carbon down here, so we can count. This is carbon 1, 2, 3, 4, 5, 6, 7, 8, 9. So from 9 to 10, you'll see the double bond there. Again, that doesn't mean from 8 to 9, it's from 9 to carbon's 10. There's the double bond. You can count the same thing over here. If I can move this little tile out of the way. Here we go. Carbon 1, 2, 3, 4, 5, 6, 7, 8, 9. So there, this is our delta 9. So the double bonds between carbons 9 and 10 of your fatty acid. So the N tells you the lower number within the double bond. So let's look at some trends in melting temperatures. So if you've ever wondered why butter's solid at room temperature, but olive oil is a liquid, it has to deal with the melting temperature of that fat. And essentially, the more saturated or the more trans fats you might have in a fat, the more solid it's going to be at room temperature. So butter has a lot of saturated fat in it, which could be natural, but it's also industrially performed. And so you'll see usually on the packaging of butter, like may contain trace amounts of trans fats or something like that. And that has to do with the hydrogenation process of taking the unsaturated fats from plants and then making them saturated. So, putting hydrogens across double bonds, thinking organic chemistry. So the more saturated the fatty acid, the higher the melting temperature. So the more solid it would be at room temperature. We're going to compare these four while we're looking kind of at some trends. So we're going to look at this stere rate. That's an 18-0. All of these actually have a total of 18 carbons. So we're holding the number of carbons within these different molecules the same. We're just going to change the number of double bonds and the type of double bond that is present. So then we have this olate, which is an 18-1, and it's a cis delta 9. So again, the 9th carbon from the carboxylic acid. So between 9 and 10, you see the double bond, and it's cis. Cis is same, so the hydrogens are on the same side. You can have this L8, L-iodate, I think, L-iodate, fatty acid. Oh, it's an 18-1, but it's also the delta 9, except for this is a trans double bond. So the hydrogens are on the opposite sides of the double bond, so trans. And then last you have the linolenate fatty acid, and that is an 18-3. So there are 3 double bonds, and those double bonds occur between carbons 9 and 10, 12 and 13, and 15 and 16. Just to note, is this an omega-3 fatty acid? Let's see. Here's carbon 1, 2, 3. Yes. So this very last one is an example of an omega-3 fatty acid. This is not. Here's carbon 1, 2, 3. Nope, single bond. This one's not. Carbon 1, carbon 2, carbon 3. Nope, no double bond there. And our fully saturated one is also not. Okay, so let's check out some trends. So saturated versus unsaturated. So saturated fats, that means that every carbon atom in the chain is saturated with hydrogens. So your saturated fatty acid has a melting point of 70 degrees Celsius. This would be solid at room temp. Room temp's like 25 degrees Celsius. So anything over 25 would be solid. Anything under 25 will be liquid. If you add one double bond, so we have a mono unsaturated. So unsaturated means that there's a double bond somewhere. This is a mono unsaturated fatty acid. This one is also a mono unsaturated fatty acid. And if it has 2 or more, you just call it polyunsaturated. So this is a last example over here is a polyunsaturated fatty acid. You can kind of see that the 3 melting temperatures are lower than the original that is saturated. So unsaturated fatty acids are going to have lower melting temperatures than their saturated counterparts. Let's look at the type of bond and see how that makes a difference. So if we look at the cis versus the trans fatty acid, what was the difference in melting temperature and why? So our cis double bond, these were both delta 9 fatty acids. So the double bonds in the exact same location. The only thing that's different is one is cis and the other is trans. So our cis compound has a melting temperature of 13 degrees Celsius. So that would be a liquid at room temperature. And then our trans fatty acid has a melting point of 45 degrees Celsius. So that would be solid at room temperature. So let's see. So why? All right. So cis double bonds put a kink within your chain. So instead of having, I guess think of it this way, when you're trying to, if you can push all these long fatty acids, so all of these carbons are freely rotating. So this, usually fatty acid hydrocarbon tails are like long pieces of spaghetti. They're just all these free rotating carbons. It can form all kinds of crazy, 3D structure. But as you're cooling it down and trying to make it turn into a solid, you can try to force these molecules together. And if you can get them to stack in very long strands, which you could for a saturated fatty acid, then you can pack them tighter and they become solid. They're more solid. So forcing a kink in the chain actually lowers the melting temperature, so it always stays a little more liquid, like that oil or whatever it is you're talking about. Those fats are more liquid. Because you can't compact them so close because you've got this hard and true fast angle in your chain, so you can't push those close together. So the trans double bond can kind of keep that long linear structure. So that's why the trans double bond is kind of acting more like a saturated fatty acid and has a higher melting temperature. But our cis double bond has that lower melting temp, and it has to deal with that kink in the chain because, again, you're trying to stack multiple of these fatty acids close to each other, but there's this covalent kink you can't get rid of. You can't force it to break and turn into a long linear species so you can get a bunch packed together. Okay, so cis versus trans. Trans will be higher melting point, cis will be the lower melting point. What about mono versus polyunsaturated fat? So we can look at the example where there's only one double bond and then the one where there's 3 double bonds. Essentially, the more kinks you have, the more that is going to want to stay liquid. So you can see that the melting temperature of this fatty acid is negative 17 degrees Celsius compared to 13 degrees. So more double bonds, the more liquid it's going to want to stay, the lower the melting temperature. Lastly, I want to talk about the essential fatty acids. So we talked about in class essential amino acids. Those are amino acids that our bodies cannot make. We actually have to get them from another source, typically plants. All plants can make these amino acids. Maybe you're saying, oh, I'll get it from eating chicken or fish or shrimp or anything like that. And essentially you could pinpoint down that all those animals consume plant products, so they're also getting their essential amino acids from plants as well. We also, though, have essential fatty acids. So there are certain fatty acids that we cannot make that our bodies require. And those are these 2 examples. So the linoleate and the linolenate. So the 18.2, that should be 18.3 right here. Excuse me, this is an 18.2, delta 9 and 12. So it's got 2 double bonds between carbons 9 and 10 and 12 and 13. And then the linolenate, which is an 18.3, would be 3 double bonds at carbons 9, 12, and 15. And the reason why these are essential is because mammals lack the enzyme that can create a double bond at that carbon 12 position. So that's why we'll have to actually consume these from either a plant or a bacterial source, because those do have this desaturase enzyme that can create a double bond at that 12th carbon position. And why are these essential? Why would consuming these fats be so important? It's because both of these fats are precursors to eicosanoids. Eicosanoids are lipid compounds that are signaling molecules. They usually work in a very small area of your body, so they're made at the site where something's occurring. So for example, if you get a cut and your blood starts to kind of clot up, that's eicosanoid. So you need those eicosanoids to signal platelet aggregation to stop bleeding. If pregnant women having those labor contractions, that's a very localized contraction, right? They're like all their muscles throughout their whole body are contracting, just kind of in that uterus area, like contracting. So those are also eicosanoids. And then you sprain your ankle and it swells up really big. That's also eicosanoid. So right at the site of the injury, these small signaling molecules, which are derived from these essential fatty acids, help, cause an inflammatory response for you. So, okay. So what are the big takeaways about fatty acid nomenclature? So you should be able to draw or identify saturated, monounsaturated, and polyunsaturated fatty acids, and be able to convert between seeing the structure and writing it in this form. Remember where it's like number colon number, it's total carbons followed by number of double bonds, and this little n should be a superscripted. But the delta would be the location of any of those double bonds. You should be able to recall the typical pKa of a carboxylic acid functional group. You'll have to be able to recall and remember oleic acid, stearic acid, and arachidonic acid. You should be able to draw or identify a cis or trans fatty acid just based off its structure. Or again, I want you to draw a cis. You should be able to draw a cis fatty acid. You should be able to identify or draw omega-3 fatty acids. You'll need to label fatty acid chains using the IUPAC numbering system. So starting with carbon 1 at the carboxylic acid all the way to whatever, and then the Greek nomenclature as well. You should be able to define amphiphilic and provide an example of an amphiphilic molecule besides a fatty acid. So find another one out there to give me an example of. And then you should be able to identify trends and melting points of different fatty acids based on their structure or based on descriptors I tell you. Like maybe I just tell you the numbers and the delta N, and then I want you to tell me which one has the lower melting point. Which one's going to be solid at room temp, which one's more likely to be solid at room temp. Oops. And then be able to recall the 2 essential fatty acids for mammals and the reason why they're considered essential for our lives. And that concludes my video about fatty acid nomenclature.